Welcome to section A-6, solving equations. So in this review material, these appendices, probably this is the most relevant. If you have trouble with the content of this section, then you're going to have trouble with the precalculus material because this is assumed background and this is about the most advanced topic from the appendices that we'll cover. All right, so the plan is, as the section title suggests, to solve equations. We'll go through various techniques and manipulations we can do to solve equations and give you some warnings along the way, some things that can go wrong and hence to be avoided. So we'll solve equations by factoring, solve equations involving absolute values, solve the quadratic equation, or solve quadratic equations by factoring, completing the square, and using the quadratic formula. The quadratic formula is often called the quadratic equation as well. But these are second-degree polynomial equations. Factoring, if you can factor, that's the way to go. We covered factoring a few sections ago. Completing the square is not an efficient way to solve equations, but the completing the square process is what we use to derive the quadratic formula. In the quadratic formula, if you can't factor, will always work. Well, the quadratic formula will work even if you can factor. Quadratic formula always works for second-degree polynomial equations. A little verbiage as we usually start these sections. An equation in one variable is a statement in which two expressions, at least one containing the variable, are equal to each other. The expressions are called the sides of the equation. We'll refer to the left side and the right side as we verbally describe the manipulations we're doing. Since an equation is a statement, it may be true or false. It depends on the value of the variable. Of course, the plan is to find the variables that make the statement true. Unless otherwise restricted, the admissible values of the variable are those in the domain of the variable. All real numbers being sort of like the universal set. Things we can't do at this stage are division by 0. So in an algebraic expression, that would be removed from the domain wherever we'd get division by 0. And square roots of negatives is the other forbidden operation at this stage. These admissible values of the variable, if any, that result in a true statement are called the solutions or roots of the equation. I disagree with the authors on the book a little bit. I'd call these solutions to the equations. The term root is usually restricted to polynomial equations, so solution is a better term. To solve an equation means to find all the solutions of the equation. The solution set is the set which contains all solutions of the equation. Will oftentimes give answers in terms of solution sets. If an equation is satisfied for every value of the variable for which both sides are defined, then the equation is called an identity. So regardless of what value the variable takes on, then the equation is true. We might have something like x plus 1 equals x plus 1/2 plus 1/2 again. Well, those are identical. They're both x plus 1. No matter what x is, that equation is true. So it's called an identity. A little boring example, maybe something somewhat more interesting, but from the realm of trig would be something of the form cosine squared x plus sine squared x equals 1. Cosine squared plus sine squared always equals 1. So that's another example of an identity, a trigonometric identity. And equations having the same solution set are called equivalent equations. The idea, sort of the big picture here, is to be given a question that involves a complicated equation and to find an equivalent equation that's simpler to solve. So you kind of simplify things and then find the variables, solve for x, as x isn't always the variable, but usually that's the case. Some procedures that produce A result in equivalent equations are the following. So these are things you can do to an equation to modify it and produce an equivalent equation that has the same solutions. Of course, you do this with a goal in mind. Usually that goal is solve for x. Get x by itself is how I'll word it. You can interchange the two sides of the equation. You can simplifying the sides of the equations by combining like terms, eliminating parentheses, and so forth. Simplifying does not change an equation. Well, produces an equivalent equation, I should say. Adding or subtracting the same expression on both sides of the equation produces an equivalent equation. Multiplying or dividing both sides of the equation by the same non-zero expression produces an equivalent equation. Of course, you can't multiply both sides by 0, because that's going to produce the identity 0 equals 0. You lose information if you multiply by 0. And of course, you can't divide by 0. That's the one thing you'll never do, is division by 0. And this actually, last comment here, is the most useful around the end of working one of these problems, if you work it by factoring. If one side of the equation is 0 and the other side can be factored, then we use the zero product property and set each factor equal to 0. We've discussed factoring in the past, and this is one. We'll solve equations oftentimes by factoring. You'll write 0 as a product of a bunch of factors. Well, the only way a product of a bunch of things can be 0 is if one or more of the things is 0. And that's how we'll deal with finding solutions by factoring. And that's probably our most common way of solving equations. A little warning about things you can't do. Squaring both sides of an equation does not necessarily lead to an equivalent equation. Squaring both sides introduces a thing called extraneous roots. For example, take the equation x equals 3. It's got one solution, x equals 3. If we square both sides, that produces x squared equals 9. But this new equation is not equivalent to the previous equation. X equals 3 has one solution, x equals 3. X squared equals 9 has two solutions, x equals 3 and x equals -3. So this equation and this equation, they're not equivalent. This has a different solution set than this one has. This one includes -3. Obviously, this one doesn't. What happens when you square both sides is you're losing sign information. If one sign were negative, the squaring loses that fact. Had that side also been positive after squaring, you would have got the same thing. You lose negative signs when you square both sides. And what's happened is we've lost the sign on x as to whether it was positive or negative, and that's how this -3 sneaks in. Be very, very careful. If you do square both sides, and the only time I can think you would want to do this is to get rid of square roots. But if you square both sides, you have to go back and check the solutions, because you've generated a new equation that has all the solutions of the original equation, but it might have more extraneous solutions, extraneous roots. So be careful when squaring both sides, or in general, when raising both sides to an even power. That's really squaring multiple times. If you do that, then you run the risk of introducing new roots. You don't produce an equivalent equation. This isn't in the list of things above. You produce a new equation. It can be a useful equation, but it must be used carefully. So let's do just a whole bunch of examples. The first three are relatively elementary. The next two will solve by factoring, and the last two will involve absolute values. So let's go to the supplemental notes and just run through a bunch of examples. All right, solve 3x equals -24 using the laundry list of manipulations we could use to produce equivalent equations. So you want to look at this, and to solve is to find x, which makes this equation true. You want to get x by itself. What you going to do? There's just 3 in the way. Well, let's get rid of it. Let's divide both sides by 3. Divide this by 3 gives us 3x divided by 3. Divide this by 3 gives us negative 24 divided by 3. Why'd you do that? To get rid of the 3 that's in the way. You take the strategy of get x by itself. So get rid of the 3. This will do it. 3x divided by 3 is simply x. Negative 24 divided by 3 is negative 8. And there's what x is. In terms of a solution set, the solution set is a set containing this solution, negative 8. So follow this strategy of get x by itself. One slightly more complicated. There's x's on both sides, but I still follow the strategy, get x by itself. Let's do this. Let's add 2x to both sides. In so doing, we'll have 0 x's on this side and all the x's will be on the right side. This then gives the equation 3 minus 2x plus 2x equals 2 minus x plus 2x. So we took the sides of the equation and we've added 2x to both sides. That produces an equivalent equation. Why'd you do that? Because on the left-hand side, the minus 2x and the plus 2x produces 0, and you're simply left with a 3 on that side. So there are no x's now on the left-hand side. On the right-hand side, the arithmetic 2 minus x plus 2x produces 2 plus x. So you're better off than when you started. There's only x's on one side now. Still following the strategy of get x by itself. What's in the way here of this 2? Well, let's subtract 2 from both sides. And then on the right-hand side, you'll simply have x. On the left-hand side, you'll have some numbers, and those numbers equal x. So subtract 2 from both sides with the strategy of isolating x. And this gives the equivalent equation. 3 minus 2 equals 2 plus x minus 2. 3 minus 2 is 1. 2 plus x minus 2 is simply x. And so we get the property x equals 1. X equals 1 is a solution. The solution set, to put it in that notation, is a set consisting of 1. So we've described this in terms of adding the same thing to both sides. There's an alternate way to interpret that. Let's look at another example. Okay. Solve for x. Good news is we've only got x on one side. I guess the bad news is there's a bunch of stuff in the way. There's a 5, there's some negatives floating around. There's 2, here's another bit of subtraction over here. So there's a bunch of stuff in the way on the left-hand side, but at least the x's are only on one side of the equation. So we simplify we simplify the left-hand side. So a typo there, I will correct that in the notes. Simplify the left-hand side to get 5 minus 2x minus 1, with a parentheses is given. Distribute the negative, giving us 5 minus 2x plus 1. 5 plus 1 is 6. That simplifies down to 6 minus 2x. So we can rewrite this, having simplified one side of the equation, as the equivalent equation. Left-hand side is 6 minus 2x equals 10. We're trying to get the x's by themselves and basically get the numbers by themselves. Get the x's on one side of the equation and the numbers on the other side. One way of doing that, not the only way, is to add 2x to both sides of this equation. It gets rid of this negative sign. We'll have to do some additional manipulations. There's other ways of doing this. But if you do that, we'll get 6 minus 2x plus 2x equals 10 plus 2x. Added 2x to both sides of the equation. The negative 2x and the 2x cancel, leaving us with a number over here. And on the right-hand side, we've picked up a 2x. Like I said, we've done this following the procedure of producing equivalent equations as encountered in the notes from this section so far. But this idea of adding to both sides, let's look what happened here. We had the equation 6 minus 2x equals 10, and we've produced the equation 6 equals 10 plus 2x. It's as if we took the negative 2x from this side of the equation and placed it on the other side of the equation, but changed the sign, changed the negative sign into a positive sign. Maybe you're used to speaking in terms of take this term to the other side of the equation and change its sign if we're adding or subtracting. And that's effectively what we've done. We might start speaking more in those terms than in this terms of the idea of adding the same thing to both sides. We'll have to speed things up a little bit. We can't do all the very minute details in any reasonable amount of time. But notice what's effectively occurred is you've taken the negative 2x from the left-hand side and made it a positive 2x on the right-hand side. The reason that works is because you've added 2x to both sides and simplified. That's the procedure that justifies those types of manipulations. Okay, we're trying to get x by itself. Well, now there's a 10 in the way. Well, get rid of it. Subtract 10 from both sides, giving us 6 minus 10 and 10 plus 2x minus 10. The 10s on the right-hand side cancel. On the left-hand side, we've got 6 minus 10 is negative 4, producing this equivalent equation. You know, we also could have said, take this 10 to the left-hand side and make it negative. Then we get 6 minus 10, 6 minus 10, which is negative 4. On the right-hand side, we'd just be left with a 2x. That idea of moving things under addition or subtraction from one side of the equation to the other and changing their sign. So we're down to here. What's in the way now with a perspective of get x by itself? The 2. So divide both sides by 2. To isolate x, divide both sides by 2. To get the equivalent equation, negative 4 divided by 2 equals 2x divided by 2. The 2's cancel, producing an x on the right-hand side. Negative 4 divided by 2 is negative 2. So x equals negative 2. Or in solution set notation, we get the solution set as the set consisting just of negative 2. All right, so there's some elementary manipulations. An idea here was get x by itself. Let's look at some that are slightly more sophisticated. Okay, here, we've got some multiplication and some squaring, and we're solving for x. I still want to get x by itself, but this multiplication is going to require us to use the zero product property. The fact that we have products here, both sides of this equation are second degree polynomials. If we were to multiply them out, we got a number of ways to approach this. One is to multiply out both sides of the equation, nothing at all wrong with that, and then simplify and solve for x. My angle here is I want to illustrate the zero product property. So I'm going to do it slightly differently. Nothing wrong with multiplying both sides out and then simplifying. Actually, it'll work out just fine. It's probably even quicker than what I'm going to do. But my agenda here is to discuss a zero product property with you. So we want 0 on one side and a product on the other side. So let's take the left-hand side, subtract it from both sides, giving us left-hand side minus left-hand side equals right-hand side minus left-hand side. We've subtracted this quantity from both sides of the original equation. That's to get a 0 on one side of the equation. It gives us a 0 on the left-hand side. On the right-hand side, we've produced this. Oh yeah, that's equivalent to taking this term to the other side and changing its sign. And as discussed previously, it's justified by the manipulations we've described. So no matter how you slice it, get 0 on one side, that will produce something of this form. How about we factor out x minus 3? There's an x minus 3 in this and an x minus 3 in that, in the first and second terms as the terms are multiplied. Then we can write the original equation in the form, the equivalent form 0 equals x minus 3 times, we factored 1 out here, so we'll be left with an x minus 3 to the first power. We factored an x minus 3 out here, leaving us with an x plus 2. Factoring is simply the distributive property backwards. If you don't believe that works, distribute, we'd get x minus 3 times x minus 3, or x minus 3 squared, right? And x minus 3 times x plus 2. We'd get this second term. So factor out, use distribution backwards. And now we can simplify this term. We've got x minus x. So those will cancel. We've got negative 3 minus 2 would produce a negative 5. This term in parentheses simplifies down to negative 5. So this becomes x minus 3 times negative 5 equals 0. I wrote the 0 on the right as we commonly do, not necessary, but it's common procedure. And I can interchange the sides of an equation, and that produces an equivalent equation. We're trying to get x by itself. Okay, well, there's some stuff in the way, and we got to get rid of that stuff in the correct order. First, there's this multiplication by negative 5. So let's divide both sides by negative 5. Do the division by negative 5. We get cancellation on the left-hand side. 0 divided by negative 5 is 0. That produces the expression x minus 3 equals 0. By the way, had you multiplied out, FOIL this, we got an equation for squaring binomials. Multiply these out and simplify, that would also have produced this. And probably more quickly. But we get an x minus 3 equals 0. Add 3 to both sides, or take the negative 3 to the other side of the equation. That produces x equals 3, and so the solution set is 3. We had x squared terms. Often when we have x squared terms, we'll get 2 solutions. We only got 1 this time. The real reason is if you simplify this, you lose the x squared term. Let's do another one with this factoring idea. Okay, this involves rational expressions, rational functions. We want to solve 1 divided by 2x plus 3 plus 1 divided by x minus 1 equals 1 divided by 2x plus 3 times x minus 1. Interesting, this denominator is the product of these two denominators. All right. Don't make up your own rules and you'll be fine. We need a common denominator. And the big idea is to simplify. So let's take this left-hand side and get a common denominator and add these together. Let's do that addition, but you can't do that addition with these quotients unless you have a common denominator. The common denominator would be the product of these two. So let's take the first one, 1 over 2x plus 3. And let's multiply it by x minus 1 over x minus 1. And that's just multiplying by 1, provided x is not 1. X can't be 1, or that gives division by 0 upstairs. So we'll keep an eye out for that. But if we multiply 1 over 2x plus 3 times this, that'll give us a denominator of the product of the two. Let's take the second term, 1 over x minus 1, and multiply it by 2x plus 3 over 2x plus 3. That'll give a denominator of the product of these two, giving us, as you see in the next line, giving us the common denominator. Okay, back up to this. We'll have a numerator of x minus 1, and we'll have a denominator of the product of these two. So this becomes that. Numerator in this second term will be the product of these two, 1 and 2x plus 3. Denominator will be the product of these two, producing this, and it worked. These two expressions have the same denominators, so we can add them together. Now, take the common denominator, add the numerators to produce a new numerator, so we get x minus 1 plus 2x plus 3 in the numerator. Let's simplify that a little bit. So far, we're only manipulating one side of the equation, the left-hand side. And that produces 3x plus 2. Yeah, 3x plus 2. Simplify. So the left-hand side, after finding a common denominator, produces this. So the original equation is equivalent to, replace the left-hand side with this equivalent expression, with this stuff here, setting this equal to that. All right, this could be a lot worse. Notice the denominators are the same on both sides of the equation. This is x minus 1 times 2x plus 3, and this is the other way around, but that doesn't matter, commutativity. So they have the same denominator. Well, if they got the same denominator, the only way these quotients can be equal is if the numerators are equal. The denominators are the same, so the numerators must be the same. So we can ignore the denominators with a word of caution. We're about to lose some information. We're losing the information that x can't be 1, nor can x be what? Negative 3/2? X can't be things that make these denominators 0. Keep that in mind. And those things are negative 3/2 and 1. If in the following manipulations we produce those numbers, negative 3/2 or 1 as a possible solution, and it doesn't look like we do, we got a problem. You can't use those. From the very beginning, we knew x couldn't be 1 because we can't divide by 0. We knew x can't be what, negative 3/2? Because we can't divide by 0, and negative 3/2 makes this denominator 0. So by ignoring the denominators and considering just the numerators being equal, it comes with some details. But be careful, you drop some information. This equation, strictly speaking, is not equivalent to that equation. This equation doesn't say x can't be 1, and this one does. It says it right there, where you see the x minus 1 in the denominator. This is a deep concept, and it's an important concept in calculus. We can't simply cancel these things on both sides and necessarily get an equivalent equation. It turns out in this case we do. Oftentimes you do, but there's some real interesting cases where you don't. Just a word of warning, we've dropped the denominators. We need to be careful about that. But we've produced this equation, 3x plus 2 equals 1. Subtract 2 from both sides. Let's speed up this arithmetic a little bit. That'll leave us with 3x on this side and 1 minus 2, or negative 1 on that side. Divide by 3, and that'll give you x equals negative 1/3. X equals negative 1/3 looks like it's the solution, and so the solution set is a set consisting of negative 1/3. My paranoia over division by 0 is well justified, but in this case, not an issue. Negative 1/3 doesn't make this 0, nor does it make that 0. Neither of the denominators are 0 on the right-hand side either. So we're okay. This is a legitimate solution, and this is the solution to that equation. Let's do some with absolute values in them. The absolute value of 1 minus 2z equals 3. Copied verbatim out of the textbook. We don't always have to use x for the variable. Let's just, for variety, let's use z. Okay, you can't just drop the absolute value. You do need to get rid of it, but you need to get rid of it in an educated way. This absolute value equation, absolute value of 1 minus 2z equals 3, is satisfied if either 1 minus 2z equals 3 or 1 minus 2z equals negative 3. Because the absolute value of 3 is 3, and the absolute value of negative 3 is also 3. So it produces two equations. I plead with you, don't just drop absolute values. I'll side with you on this. You don't want them there, but you can't just drop them. You can get rid of them, but you have to know what you're doing to get rid of them. You can't simply drop them. This would be an excellent pre-test question, because if you just drop those absolute values, you don't get the right answer. Well, that's commonly the case. So eliminating the absolute value in an educated way produces two things, either 1 minus 2z equals positive 3 or 1 minus 2z equals negative 3. Remember, you're going to take the absolute value of 1 minus 2z. In both cases, again, that produces 3. So let's solve both of these equations. So we find the solutions by solving these equations separately, solve both of these equations. For 1 minus 2z equals 3, we'll take the 2z to the right-hand side where it becomes positive. If you let me speak that way. Take the 3 to the left-hand side where it becomes negative, giving us 1 minus 3, which is negative 2. Divide both sides by 2, giving us z equals negative 1. If that was a little fast, pause or rewind and watch it again. We do need to speed up these computations a little bit, but you got the time to pause and rewind and think it through. These are legitimate manipulations, just sped up a little bit. The other equation, 1 minus 2z equals negative 3. Same idea. Let's take the 2z to the right-hand side where it becomes a positive 2z. Let's take the negative 3 to the left-hand side where it becomes a positive 3. 1 plus 3 is 4. 2z on the right-hand side. Divide by 2. We get z equals 2. So we've got two solutions. Either z equals negative 1 or z equals 2. Verbally, there's a solution. And so the solution set for the first time consists of more than one thing. It's the set consisting of negative 1 and 2. Don't just drop the absolute values. If not me, somebody else in your freshman calculus or pre-calculus classes is going to be looking for you to do exactly that. You take multiple choice test, it's a predictable error, so don't make it. Treat the absolute value with the appropriate respect, and you'll get the right answer. Okay, another one. Dealing with, actually, I want to cover some more notes first. Let's go back to the notes. Okay, so we made it through all of those. We want to deal with second-degree polynomial equations. We want to derive the quadratic formula, as it says near the bottom of this page. A quadratic equation is an equation equivalent to the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers and a is not 0. A is not 0 means you really do have an x squared term. As b could be 0 and you might not really have an x term, but you have to have a x squared term to have something that's referred to as a quadratic. The quadratic equation in this form, ax squared plus bx plus c equals 0, is said to be in standard form. The quadratic equation is also called a second-degree equation because it involves the second power of x. It's related to a second-degree polynomial. This is a degree 2 polynomial because the highest power of x is 2. A little verbal comment. This book is going to refer to this formula as the quadratic formula. And many people, myself included, are likely to also call this the quadratic equation. In the verbiage of this book, strictly speaking, this is a quadratic equation and this is the quadratic formula. I'll do my best to use the verbiage correctly, well, consistently with the book, but I'll probably mess it up a time or two. So we're headed to deriving this. Now let's look at 3 more examples, and then we'll derive the quadratic formula. Okay, solve x times x plus 1 equals 12. All right, I want to get x by itself. That's going to be a wee bit of a challenge because we're dealing with a quadratic this time. There's an x squared term when we multiply out. So let's multiply out. Multiply the left side out, x times x plus 1, distribute x squared plus x. So the given equation is equivalent to the left-hand side's x squared plus x equals 12, or let's put it in standard form, x squared plus x minus 12 equals 0. Take the 12 to the other side, change its sign, or subtract 12 from both sides. We want to solve this. Can you factor this over the integers? If you could factor this, just stated what the factoring is, but here's the intermediate steps. This means you need to find, in the verbiage we used in Appendix A3 on polynomials, we need to find a lowercase a and a lowercase b such that the product of those two is negative 12, and the sum of those two is 1, the coefficient here. Product is negative 12. You're going to get 12 by multiplying 1 and 12, or 2 and 6, or 3 and 4, plus or minus as appropriate. So that gives us, I think, about 6 options on that. And then we want the sum to be 1. Well, among all of those pairs that lead to a product of negative 12, say a equals negative 3 and b equals 4 is the one that will give us a sum of 1. Take this as a and this as b. A times b equals 12. A plus b equals 1. Did I say that correctly? A times b is negative 12, and the sum is positive 1. So we did some of those in detail back in Appendix A3 on polynomials. Let's go ahead and observe that this is how it factors. Granted, I skipped some steps on that, but here's what we get in terms of factoring. So we had this x squared plus x minus 12 set equal to 0. We factor it and set that equal to 0. Now we got a product of two things that equals 0. So we can use the 0 product property to say that means either the first thing equals 0, x minus 3 equals 0, or the second thing equals 0. And I stand by my original claim. You're trying to get x by itself. We just need a little more equipment to get x by itself in this one. We've produced these equations. The solution to this, if you like, take the negative 3 to the other side. We get x equals 3. Take the 4 to the other side. We get x equals negative 4. X equals 3 and x equals negative 4. There's the x's by themselves. These give us the solutions, and the solution set consists of either negative 4 or positive 3. So we've solved by factoring ultimately, and we use that factoring along with a 0 product property to produce two equations from which we can isolate x. Get x by itself was still the big picture. Solve for x. Okay, it was a little more complicated in this case. It's because it's a quadratic that we're dealing with. There's an x squared involved in this one. We dealt with a couple of questions ago something that had an x squared in it, but it seems the x squared disappeared in the manipulations. Here it doesn't disappear, and that's the reason we get two solutions. Let's do another one. Solve 3x minus 2 squared equals 4, and you're explicitly told to do this by taking square roots. Well, there's a square. We'll take a square root. We'll get rid of that square. Yeah, if we're careful. We'll also introduce an absolute value. So let's take square roots of both sides. Square root of 3x minus 2 quantity squared equals the square root of 4. But 3x minus 2 quantity squared, square root of, when you take the square root of something squared, you get the absolute value of the something. Remember, square root of something, x, a, whatever. The square root of something squared is the absolute value of the something. I'm using the word something in the place of x here. We stated this back in the first appendix. So we've got this stuff squared, square root of, we get the absolute value of this stuff, the 3x minus 2. So taking square roots produces this. It's a second degree polynomial. I'm expecting up to 2 solutions, and the absolute value will produce 2 solutions. So take square roots like you were told to do, and treat the square roots and the squares with appropriate care to produce an absolute value and then treat that with appropriate care. So the original equation is satisfied if either 3x minus 2 equals positive 2 or it equals negative 2, because the 3x minus 2 is in the absolute value of 2 equals 2, and the absolute value of negative 2 also equals 2, produces two equations. These equations will get x by itself in the usual way. 3x minus 2 equals 2. We'll add 2 to both sides or take the negative 2 to the other side, producing 3x equals 4. Then we'll divide by 3 to get rid of that coefficient to get x by itself, and we get x equals 4/3. The other equation is dealt with similarly, except this time when we take the negative 2 to the other side, we get a 0. We get negative 2 plus 2, or if you like, I can cancel those negative 2's. Be careful with that cancellation stuff idea though. And we get 3x equals 0, divide by 3, and we get x equals 0. So two solutions, x equals 4/3 and x equals 0. X equals 0 and x equals 4/3. The solution set is 0, 4/3. When I write these solution sets, I'm probably going to put the numbers in order, from lesser to greater. You ain't got to do that. It's a nice thing to do for consistency. It'll be useful down the road to have these solutions written in order. I can't demand it of you because it's a set, and sets don't have orders. There's not a first thing in the set and a second thing in the set. There's just stuff in the set. The stuff in this set is 0 and 4/3. I could also say the stuff in this set is 4/3 and 0. But it will be convenient later to have these listed from lesser to greater. But it's not necessary, but it will be useful later. It's a good habit to start. Another one involving a quadratic. This one's going to be a little awkward. So solve this 2x squared minus 3x minus 1 equals 0 by completing the square. All right. Completing the square. We did that in, I think that was done in section A.3. And the reason we did that was to derive the quadratic equation, which means we did that ultimately to solve second-degree polynomial equations. So this is going to be awkward. The only one of these we're going to do. Next, we'll derive the quadratic formula, and the quadratic formula applies to this question. All right, well, let's do what we got to do. We're motivating the way we will derive the quadratic equation, the quadratic formula. First, let's take 2x squared minus 3x minus 1, take this left-hand side, and let's manipulate it. Let's factor a 2 out, because I said so, that's why. Leaving you with 2 times x squared minus 3/2 x minus 1/2. Notice if you distribute the 2 back in, we get a 2x squared as we should. Get a 2 here, those will cancel, leaving us with a minus 3x as it should. Distribute here, 2 times negative 1/2 is negative 1 as it should be. Now, the reason we've done that is to get within these parentheses a coefficient of 1 on the x squared. Because in our completing the square formula, we have something of this form. It was x squared minus bx. If you have something of that form and you add just the right thing, you'll produce a perfect square. Well, we do have something of that form. We've got x squared minus bx right there, looking at this piece of it. And to have a 1 in front of the x squared. That's why we factored out the 2. So we get an x squared minus 3/2 x. That's going to behave like this. We wish to add exactly the right thing to that to produce a perfect square. Back when we explored completing the square, we observed if you add 2x squared minus bx, b over 2 squared, you'll get a perfect square. What you'll get is x minus b over 2 squared. We consider these cases where we had either a positive sign or a negative sign here. We actually had 2 statements of this, but this is the one with a negative sign in it, and we've got a negative sign right there in front of b. B will be 3/2. We take b equal to 3/2. then b over 2 will be 3/4, and b over 2 squared, looking for this, will be 3/4. Oops, missing an exponent on that. 3/4 squared equals 9/6. 3 squared is 9, 4 squared is 16. My apologies. I'll correct this in the online notes. There's an exponent of 2 missing there. So we need to add 9/16 to this to get a perfect square. If we take this, x squared minus 3/2 x, I know it's just a piece of it, and if we add 9/16 to it, we'll get the perfect square, x minus b over 2. We said b over 2 was 3/4 upstairs, right? X minus b over 2 squared, x minus 3/4 squared. Foil it out and you see that it works. All right, but there's a bunch of other stuff going on. We've just been concentrating on this part of it. So let's take the original equation, which we've written in this form. We factored the 2 out. Here's the very original left-hand side. We factored the 2 out. Now we want to add a 9/16 to this. So do it. Add a 9/16. You can't just add a 9/16. That changes everything. So let's subtract 9/16 at the same time. So we've really just added 0. But I want to collect these terms together because that is a perfect square. Know what I mean? X squared minus 3/2 x plus 9/16. That we saw above, since we've completed the square, is a perfect square. X minus 3/4 squared. So this part becomes x minus 3/4 squared. We picked up that negative 9/16 to keep the books balanced, to keep the equality right there. And we still got the negative 1/2 hanging on from here, and the 2 still out front. So this is equivalent to the original equation. Seems like an awkward way of doing it, but that's the way they told us to do it, by completing the square. We completed the square. How about we simplify this a little bit? Common denominator would be 16. So multiply this by 8 over 8, and this would become 8/16. Then we'd have negative 9/16 minus 8/16. Negative 9 minus 8, negative 17/16 is what that produces. And the original equation had right-hand side 0. So this is equivalent to the original equation. We've got 0 on the right-hand side. What an inefficient way to work a problem, but we're motivating the quadratic equation here. How about this? Let's try to get x by itself. Now that we did that completing the square thing, get x by itself. All right, let's divide the 2 out. Take this equation, equivalent to the original equation, divide both sides by 2. You simply lose the 2. Produces this. Let's take this negative 17/16 to the right-hand side. It becomes positive. Add 17/16 to both sides, and that produces this. All right. You might want to pause and convince yourself that all the claims on this slide are true. This is equivalent to the original equation. Let's go to the next slide and reproduce that last thing we derived. So here's the last thing we had right here. You know, that looks kind of like the previous example that we saw by taking square roots. So let's do that. Let's recycle information. Do it the same way. Take square roots of both sides. All right. Square root of something squared, as you've been warned, produces an absolute value. Take the square root of both sides. Right-hand side is some number. We can simplify this a little bit, and we will. But left-hand side being a square followed by a square root produces an absolute value. So with the absolute value of x minus 3/4 equals the square root of 17 over 16. Square root of the quotient is the quotient of the square roots, and the square root of 16 is 4. The square root of 17 you're pretty much stuck with. So we get the absolute value of this equals square root of 17 over 4. So it must be that this is either positive square root of 17 over 4 or this is negative square root of 17 over 4, because the absolute value will absorb that negative sign. That produces two equations. X minus 3/4 equals, verbally to emphasize, positive square root of 17 over 4, or x minus 3/4 equals negative square root of 17 over 4. And these two equations, these are elementary equations. They're easy enough to solve. It's got this weird square root of 17 in it, but whatever. Let's solve the first equation. Add 3/4 to both sides. Take this negative 3/4 and put it on the other side. It becomes positive, same thing. Produces this. Fortunately, they already have the same denominator. We can combine those to produce x equals 3 plus the square root of 17 divided by 4. The other equation is quite similar. Take the 3/4 to the other side, produces this, common denominator, and gives another solution of 3 minus the square root of 17 over 4. The two solutions are x equals 3 plus the square root of 17 over 4, and x equals 3 minus the square root of 17 over 4. And I could express this in a combined way as x is of the form 3 plus or minus the square root of 17 over 4. And that rings a bell related to the quadratic formula. The quadratic formula, which I'm suspecting you've been exposed to before, yields solutions that looks like that commonly. Let's play with this a little bit more. So combining, as I said, we get x equals 3 plus or minus the square root of 17 over 4 is the two solutions. If you'll let me combine them with a plus or minus, if I write it as a solution set, I'll separate them out. Here's the lesser, here's the greater, and there's the solution set. Okay, that was the ugliest problem we've done to date. There's an easier way of doing it. As we'll see, when we have the quadratic formula, this original quadratic equation in standard form has ax squared plus bx plus c. A is 2, b is -3, c is -1, as it states down here. If we plug that into the quadratic formula, I know yet to be stated, but this is what it is. You plug those numbers in, you simplify, you get the same thing. That is easier than what we just did. Question is, where does that come from? Let's figure that out. So briefly back to the notes. The quadratic formula in solving second-degree polynomials makes completing the square no longer necessary. So it's a useful thing, and it's way quicker than completing the square. To justify it, we have to complete the square. So one last big episode of completing the square. Consider the quadratic equation. Ax squared plus bx plus c equals 0, where a is non-zero. In other words, there really is an x squared term. If b squared minus 4ac is less than 0, then this equation has no real solution. If b squared minus 4ac is greater than or equal to 0, then the real solution or solutions of this equation is, or are, given by the quadratic formula. X equals -b plus or minus b squared minus 4ac over 2a. This quantity under the radical, the b squared minus 4ac, this is called the discriminant. We'll make a comment about real solutions and so forth, but let's go through and establish this. So we want to take this equation and solve it and show that x is of this form. We just did one like that. And the one we just did was a little clunky. This one will be a little clunky too. I don't know what the numbers are. They're represented by A's, B's, and C's. But the manipulations are exactly the same in this question 92 here. So let's take the quadratic equation, ax squared plus bx plus c equals 0, where a is non-zero, and let's manipulate it. I want to complete the square. By completing the square, we'll be able to take some square roots of a square and isolate x. I stand by my previous claims. We're still just trying to get x by itself. Okay, it's a bit more complicated this time, especially with these letters. But what we're about to do with A, B, and C is the same thing we just did in that previous one where we had was it 2 and 3/2 or something like that. But it's the same manipulations, just with letters. Let's divide both sides by A. In so doing, ax squared divided by A is simply x squared. B over A, C over A, splitting it up, simplifying, we get something of that form. You can't divide by 0. We divided by A, and A is not 0. We were told in the beginning. This is like when we factored the 2 out in the previous example. I want a 1 in front of this x squared. Why is that? So we can complete the square. So we're going to complete the square on this. Next slide, we'll repeat this last statement. So there's the last statement. Let's take the c over a to the other side. It becomes negative. Subtract c over a from both sides. All right, this, we can complete the square on this. How's that? You take the coefficient of x, divide it by 2, and square it. Passing comment here. When we dealt with completing the square, we had something of the form x squared plus bx. Unfortunately, they use a symbol b there. We've got a b here, but it plays a different role. To complete the square in x squared plus something x, add something divided by 2 squared. Previously, the something was a b. This time, the something is b divided by a. I read it quickly as if it were one thing. It is one thing. It's b divided by a. So we have x squared plus b divided by a, x. To that, we add b divided by a over 2 squared. Take the coefficient of x, divide it by 2, and square it. Add that to both sides. You can't argue with the validity of that. We're adding the same thing to both sides. The motivation, well, this time you can't argue with a motivation. This is going to be a perfect square because we've completed the square. Simplifying a little bit more, b divided by a divided by 2 is b over 2a. Square that, we'll get b squared over 2a squared, which is 4a squared. Simplify and square both sides. So all we've done is expand this little thing in parentheses and simplify. Square it and simplify the compound fraction. This is a perfect square. This is x plus b divided by a over 2. Quantity squared. So we get this square equals that. If you don't believe it, FOIL it out. And indeed, that's what you'll get back. We guaranteed this would work because we added just the right thing to make that a perfect square. We completed the square. Right-hand side, we didn't do anything there just yet. Well, we probably should. So we've got the perfect square on this side. By the way, my perspective is get x by itself. Okay, we're closer. I mean, there it is. It's got some stuff added to it, and it's inside a squaring function. But notice the right-hand side. This is just numbers. Well, it's not x's, and we're trying to get x by itself. Granted, it's letters, but the letters represent constants. Let's get a common denominator on the right-hand side. Denominator here is a, here is 4a squared. So if we multiply this by 4a divided by 4a, that'll give a denominator of 4a squared, and we'll pick up a factor of 4a in the numerator. We've multiplied by the appropriate thing to get a common denominator on the right-hand side. Next slide should reproduce this equation. Yeah, now let's add those together. Let's see, was I misreading? Where'd this negative sign come from? There it is. I think I failed to read the negative sign in some of this, but we had the negative sign. It was introduced up top. Negative carries over. Well, that's important. Let's add these together. Let's put the b squared first and the minus 4ac second. That sounds familiar. B squared minus 4ac. It was the discriminant. But I can put this in any order I want as long as I'm careful with the plus and minus signs. Let's write it as b squared minus 4ac. We got the common denominator. We're good to go. That gets divided by 4a squared. So simple manipulations, getting a common denominator and adding together and changing the form of it. Let's take square roots of both sides. Take the square root of this side, you'll get the absolute value of this. Take the square root of that side, we get the square root of this. This might be negative for all we know, because I don't know anything about A, B, and C. There's a possibility this is negative, and that'll cause some problems, and we'll deal with that shortly. But take a square root of both sides, produces a square root on this side. On this side, produces an absolute value. We can get rid of the absolute value by considering the positive square root or the negative square root, the square root method. So same thing we did previously. We just didn't write the absolute values out this time. So we get something of this form. Take the b over 2a to the right-hand side. It becomes negative, produces this. I want to add these together. Should do anything about that. Square root of the quotient is the quotient of the square roots. We discussed that in the section on rational expressions, I think it was. Square root of 4 is 2. Square root of a squared is the absolute value of a. After all I went through warning you not just to drop absolute values, it looks like I'm just dropping absolute values, but I ain't. If a is positive, I can drop absolute values. And we'll get negative b over 2a, plus or minus this, with that replaced with a itself. If a is negative, then we'll get negative b over 2a minus or plus. Right? We'll have a negative sign come out from the absolute value. We'd get a negative a out for the absolute value, which is itself positive if a is negative, but a negative would come out, and this would become a minus or plus. Well, in the end, we get the same two solutions. The plus or minus stuff takes care of the fact that if a is positive or a is negative, the absolute value generates potentially a negative sign, but it's absorbed by this plus or minus. Technically, in one case, it's a minus or plus, but it's the same two numbers. We've got two numbers out of this, assuming we're not taking square roots of negatives. If we are taking square roots of negatives, we still got two numbers out of it. It's just a couple of them are complex numbers, potentially. So now we've got a common denominator. Next slide. This is what we had. Let's add those together, combining the denominators since they're the same. And we get x equals negative b plus or minus square root of b squared minus 4ac. And that's exactly what we were supposed to get. So there's the quadratic formula. This thing about b squared minus 4ac, if this is greater than or equal to 0, then we're not taking square roots of negatives. If the discriminant, let me throw the vocabulary at you a little bit. If the discriminant is non-negative, we're not taking square roots of negatives. If the discriminant is 0, this will just drop out. If b squared minus 4ac equals 0, this disappears. And we get x equals negative b over 2a. If it's positive, then we get two numbers here. We get two little positive numbers from the square root, which are then added or subtracted. And that's the reason we get two solutions if the discriminant is positive. One solution if the discriminant is 0. And as we'll deal with it, if you're taking square roots of negatives, we don't get any solutions because we're not using complex numbers. If you would use complex numbers, then you get two solutions. It turns out, if you count the right way, you always get two solutions for a second-degree polynomial. When the discriminant's positive, we'll get two real solutions. When the discriminant is 0, we'll get one real solution, but in a sense, it counts twice. It's said to be of multiplicity 2. And if the discriminant's negative, then you get two complex solutions. So you always do get two solutions, but you got to let me use complex numbers for that to hold. So there's a derivation of the quadratic formula. We'll use this and pretty much abandoned the completing the squares. The completing the squares was brought up to primarily to do the derivation of the quadratic formula. There might be some other exotic settings that come along in your travels where you want to complete the square. It won't be common though. The primary purpose was to get the quadratic formula. Okay, this thing about the discriminant, I really just discussed all of this. If b squared minus 4ac is greater than 0, then this equation will have two real solutions given by the quadratic formula. If the discriminant is 0, we get one solution, but it's repeated. It's a double root. This has got to be the book's verbiage. I wouldn't say it quite like that. It's a solution of multiplicity 2 is common verbiage. And if b squared minus 4ac, if the discriminant is negative, less than 0, there's no real solutions. And it turns out there's two complex solutions. So if you let me talk about complex numbers, there's always two solutions. You just got to allow complex numbers and count in a clever way in the second case. It turns out if we use complex numbers, every quadratic equation has two solutions. So as I was saying, this is a result called the fundamental theorem of algebra. I mean, the name of this class is Precalculus 1, parentheses, algebra. Precalculus 2 is about trig. So this must be important stuff. It's the fundamental theorem of algebra. Unfortunately, to have a conversation about that, we've got to have a conversation about complex numbers. So we'll probably look at that in section 4.6, but from a pragmatic point of view in the class, we probably won't have time to do very much. We won't cover 4.6, but we got to look at the fundamental theorem of algebra. Geez, this is an algebra class. So let's illustrate the quadratic formula with three final examples. Use a quadratic formula to find the real solutions, if any, of this equation, this quadratic equation. As I said, I'll probably muddle the verbiage a little bit between quadratic formula and quadratic equation. I'm quite used to calling this a quadratic equation. Book's verbiage is quadratic formula, and that's a quadratic equation. Coefficient of x squared is 2, coefficient of x is 5, constant term is 3. We've denoted those as A, B, and C in deriving the quadratic formula. We could take this equation, divide the 2 out, complete the square, do all those manipulations, and we get the same thing as follows. We've done that. We're burying all that, completing the square stuff in the quadratic formula. So applying the quadratic formula, negative b plus or minus b squared minus 4ac divided by 2a. B is 5. Put a 5 there and there, 5 there and there. I've put parentheses around things that are substituted in. A is 2. Put a 2 there and there, a 2 there and a 2 there. C is 3. C only occurs in one spot, like I said, and this is consistent throughout the notes. Things that I've substituted in are in parentheses. The 4 is not in parentheses. The 2 is not in parentheses. Well, I didn't substitute in to produce those. The 4 came from here and the 2 came from there. Doing the arithmetic, we get negative 5 plus or minus. 5 squared is 25. 4 times 2 times 3, that's 8 times 3, that's 24, negative. So we'll have 25 minus 24, square root of 2 times 2 is 4 in the denominator. 25 minus 24 gives us the square root of 1, which is 1. And we get negative 5 plus or minus 1 over 4. There's an acceptable expression for the solutions. There's 2 of them because of the plus or minus. Let's explicitly figure out what they are, though. If we take negative 5 plus 1 over 4, that'll give us what? Negative 4 over 4, negative 1. If we take negative 5 minus 1, so here's the plus case and here's the minus case. We get negative 5 minus 1 is negative 6 over 4. That simplifies a little bit, the negative 3 has. So there's the solutions. More explicitly, -1 and -3 halves, and here's a solution set, -1 and -3 halves. So there's an application of the quadratic equation, quadratic formula, and that was a bunch easier than completing the square. We did the completing the square so we could make this easier and use the quadratic formula. Let's do another one. Use a quadratic formula to find the real solutions, if any, of x squared plus square root of 2 times x minus 2 equals 0. Okay, it's a quadratic equation. This is where a equals 1, b equals the square root of 2, and c equals -2. So we'll apply the quadratic formula. X equals -b plus or minus square root of b squared minus 4ac over 2a. b square root of 2 here and here. A is 1 here and here, here and here. C is -2. C only occurs over there. Same little story. The things in parentheses are things I've substituted in for. And let's simplify. Square root of 2 squared is 2. -4 times 1 times -2 is +8. 2 plus 8. All right, we'll drop those parentheses there. 2 times 1 in the denominator is 2. That gives us the square root of 2 plus or minus the square root of 10 divided by 2. You simplify that. I could manipulate some things with square roots of 2s. I'd get an irrational denominator. This is good enough. So we get that x is either negative square root of 2 minus the square root of 10 over 2, or negative square root of 2 plus the square root of 10 over 2, the plus or minus cases. And as a set, we get the solution set as given here. Straightforward, same thing as before. The only thing that's a little bitty bit more complicated is you had this square root stuff arise. But just deal with square roots. Square root of 2 is a square root of 2. I know what happens when I square it, but I don't have a precise value for it, and I certainly don't want to approximate this. We can give precise values. If you're doing an applied problem, an engineering problem, or a physics problem, and you want numerical approximations, well, you'd still have to do all of this. Then you got to pick up the calculator or the software and see what these are to a dozen decimal places. Let's just leave it precise. This is a math class, not an accounting class. And a final example, use the discriminant to determine whether this quadratic equation has two unequal real solutions, a repeated real solution, or no real solution without actually solving the equation. So what they're asking you really is, what's up with the discriminant? Is it positive, 0, or negative? And we just saw what happens in those three cases. We have a equals 2, b equals -3, and c equals -4. Take these parameters, the discriminant, b squared minus 4ac is then, b is -3 minus 4a is 2, c is -4. -3 squared is 9, -4 times 2 times -4 be positive. 8 times 4 is 32. Yeah, 9 plus 32 is 41. The discriminant's 41. The important thing about 41 is it's positive. If the discriminant is positive, we'll have -b plus or minus the square root of 41. That'll generate two solutions. The positive, the plus square root of 41 solution, and the minus square root of 41 solution. That'll generate two unequal real solutions. Again, that's what we said in note 8.6.c. That's what we get by considering the discriminant. If it's positive, two unequal real solutions, and it would be not very complicated to find what those solutions are. But I can look simply at the discriminant and determine the nature of the solutions without actually finding the solutions. And that takes care of section A6, solving equations. And there's a couple more sections at the end of this Appendix A stuff that is also fairly essential for Precalculus 1. There's dealing with inequalities and dealing with rational exponents, I think. They're short sections. But these first 6 sections, with the exception of, I think there's a section on synthetic division, which we don't need. But these first 6 sections, excluding the synthetic division, along with the last couple of sections of Appendix A, these are essential things for Precalculus 1. This one being the most important of the appendices, in my opinion. So I'll catch you later, and we'll come back and look at some of those other sections as mentioned. Have a nice day. I'll see you later.